This is the last lecture in this topic, the stellar archaeology and near field cosmology. Here we are going to focus on the first stars, how stellar archaeology help understand their nature. So this is the old slide showing the cosmic timeline. So after the Big Bang, the universe expands and cools, and there are brief dark ages, and once the universe cools and facilitates formation of molecular hydrogen, the first stars form, and the first stars make the first metals in the universe, and they also reionizes the universe. So here is the overview of the talk. So we are going to discuss what are first stars, theoretical and observational perspective, how do they impact the structure and evolution of the universe, when and where do they form, and how to find them. So what are first stars? By definition, we can think they are stars which are formed early in the universe, and there are also working definition which says stars that are formed from a cloud that is purely of primordial matter. That is, it consists only of hydrogen, helium and trace amount of lithium that was made in Big Bang. So in principle, if these stars could be seen or formed even at lower redshift if there is inefficient mixing of the ISM. So you could see POP3 stars forming at different varied redshifts and different environment. So these first stars end the dark ages and reionizes the universe. They also produces the first metals, and these first metals are efficient coolant and would enable formation of low mass stars. And on the theoretical perspective, so it is thought that first stars which is made of purely hydrogen and helium and zero metals, they are expected to be inefficient in cooling because pure hydrogen is not efficient in cooling, and molecular hydrogen does not have a dipole moment. So formation and as a coolant they are quite inefficient. So a warmer gas would form massive stars. So the expected first star masses are about 100 to 500 solar masses, and the entire cloud collapses adiabatically without fragmentation, and this leads to formation of really big stars. So forming the first stars, how it differs compared to the present day star formation. So the primordial gas has no heavy elements, and the typical efficiency of the cooling and the temperatures are expected to be of 10,000 Kelvin, and only when hydrogen molecule can form, that is the only way the gas can cool. However, the present day gas, even with a trace amount of heavy elements up to about 2%, they are excellent radiators of heat. So they efficiently cool, and the typical cloud temperatures are about 10 Kelvin. So these present day molecular clouds fragments and form small stars. The necessary condition for fragmentation is that cooling time scale should be much shorter than the free fall time scales. So this implies the minimum mass, that critical mass of the dark matter halo for star formation at each redshift is going to be different. So in summary, a hotter gas would make massive stars. So this is a schematic diagram, and I think a snapshot of a simulation, and it shows the formation scenario of first stars. So on the left, what you see is the protogalaxy. It starts with a mixture of dark matter and ordinary matter. So the dark matter is shown in red and the ordinary matter is shown in blue. So, once molecular hydrogen forms, the baryonic matter start to cool and start to condense, and they become centrally concentrated. And the centrally concentrated baryonic matter forms the first stars. So, the typical masses of these are about 100 solar masses, and these are formed inside a mini halo of 10^6 solar masses. And the radius is about, these mini halos have a radius of 100 parsecs. Yeah, this is again to show a different, the first stars form at different environments. So, you could see at first stars at different redshifts are shown. So, you would see the first stars start to form at the density peak. So, it is represent the central regions of the galaxy. And first stars also start to form at later in the redshifts in the outskirts, especially in the halo and smaller galaxies or smaller, less dense subhalos. So, it is important to study the metal poor stars in the different parts of the galaxies to understand first star formation at different conditions. So, on the observational perspective of first stars, so if first stars are massive, then they are long gone. So, if we need to observe them, we have to observe them at high redshifts. So, possibly with the future space and ground based telescopes like JWST or TMT and ELTs. So, if the first stars are low mass, then it should be detectable in Milky Way. So far, zero metallicity stars are not observed in the halo, and so accretion of metal rich ISM can increase the metallicities to some extent. The indirect evidence of first stars can also be seen through ionization of hydrogen, and this is one of the primary goals of the square kilometer arrays. The nature of high redshift gamma ray bursts and supernovae, they also can probe the nature of the first stars, and their properties across various redshifts can tell us the property of these massive first stars at different environment. So, theory predicts pair instability supernovae to be predominant during these early galaxies. So, cosmic evolution of metallicity, heavy elements will also be influenced by the nature of the first stars. So, the properties of first stars, they are massive as we said. So, the nuclear burning initially they start with pp chain, so which is inefficient, and at higher temperature the triple alpha reaction start to produce the first heavy elements, and once triple alpha reaction forms carbon, then the hydrogen burning starts with the CNO cycle, and convective interiors and radiative envelopes. So, this would produce the varied kind of odd elements in the first stars. So, the only effective opacity at this stage for the POP3 stars are due to electron scattering. So, low metallicity, low opacity and high temperature can make these stars much bluer than the solar metallicity counterparts. So, the lifetime are about 3 million years, and as the luminosities goes with the mass. So, this plot shows for two metallicities the evolutionary tracks. You can see that the blue curve which shows the evolutionary track for zero metallicity massive stars or first stars of different masses. You can see them to be more brighter as well as bluer compared to the metal rich counterpart. So, what are the final masses of these first stars going to be? So, this plot shows the initial masses and the final mass. So, we can see that stars which are up to from 10 to 100 solar mass, they end up as a supernovae. Between 100 and 150, they end up as a pulsation pair instability supernovae, and up to 300, they become pair instability supernovae. And beyond that, all these stars end up into a directly falling back as a direct collapse of a black hole. So, you can see the pair instability supernovae which leave no remnant, and the entire star explodes and produces a lot of synthesized heavy elements to the universe. So, these are the properties of the pair instability supernovae. They are found to be predominant during low metallicity environment, and they are energetic, and they can be detectable at high redshifts. And so, they also eject lot of heavy elements and enrich the metallicity very rapidly, and this could be seen in the statistics or the number of metal poor stars in the Milky Way. They also have a peculiar abundance pattern, very different from normal supernovae. They also produce dust, which is efficient in cooling and producing small stars, but unfortunately, no pair instability supernovae is seen so far. So, we will also see that chemical abundances of metal poor stars do not show significant pollution by pair instability supernovae. And this is showing, we are showing it again. So, the peculiar abundance pattern, which is the odd even effect, which is seen by a pair instability supernovae ejecta. So, one of the clear indication or observational constraint of the first stars is the metallicity distribution of the metal poor stars. So, the plot here we show various observations, satellite stars from the ultra faint satellite dwarfs, and Milky Way halo, and dwarf spheroidal, and you can see significant tail in the metal poor end. So, which does not agree with the pollution significant contribution from pair instability supernovae. An ejecta from a pair instability supernovae produce solar metallicities. So, any star below -2 may not be seen if a significant pollution of pair instability was present in the early epoch of the galaxy. So, this is again a theoretical simulation showing the abundance pattern of a pair instability supernovae for various dilutions, and you can see they produce even with a huge amount of dilution, still the ejecta is metal rich. And this is a plot on the right hand side, shows a best fit IMF for a range of metallicities seen in the extremely metal poor stars. And so, what is seen here is the best fit is achieved for a median mass of 20 solar masses for the supernovae. So, we also looked at, this is also interesting to see, the critical metallicity and formation of low mass stars. So, if we have not seen any low mass stars as POP3, there could be a ceiling in the metallicity to the formation of low mass stars. And it is also interesting to see the transition of massive first stars to low mass stars, whether it happened abruptly. So, this is a work which shows indeed in terms of carbon and oxygen, because they are the most efficient coolant, there is this zone of forbidden where we do not have any metal poor stars. So, though we have metal poor stars up to metallicity of lowest metallicity of -7, still most of them are found to be carbon and nitrogen and oxygen rich. So, if we include carbon and oxygen as an important coolant, then we would see a forbidden zone. There are no stars which are seen, the extremely metal poor stars seen at lower metallicity below -3.5. So, this indicates possibly there is a metallicity ceiling for forming low mass stars. So, this is the current picture of the Milky Way. It is from the Gaia satellite. So, we can see the complex structure of the Milky Way. So, it is a illustration which shows the disk of the galaxy, and you see the hot bubbles, and also the Sagittarius dwarf galaxy, which is spanning the entire halo of the Milky Way. And there are several small ultra faint dwarfs seen in these Milky Way satellites. So, to get a comprehensive picture of the formation of the galaxy and first stars that form, which contributed to the enrichment history of the galaxy, we need to study the Milky Way satellites and the neighborhood, and how the accretion history of Milky Way changed the distribution of metal poor stars. So, this involves a large effort, spectroscopic effort, surveying large volume of the sky. So, that brings to the ambitious future surveys which are planned. And so, this is the Monarchia Spectroscopic Explorer project. This survey can probe individual stars, it can take spectra of individual stars up to 300 kiloparsecs. That covers majority of the local dwarfs, and it can take spectra of all the known streams of the Milky Way, and it can observe M31. So, it's going to provide a complete picture of the mass assembly of the galaxy. And the survey also has various other capabilities, like both lower and higher spectral resolution. So, it can probe many of the open problem in the field of stellar archaeology. So, this kind of shows various key elements which are chosen for studying in the survey, and so it can identify huge lot of R process rich stars, and the evolution of R process at different metallicities, which are huge number of samples. So, we would be able to identify statistically significant groups of these different low metallicity stars, and probe the sites of the first stars. And so, this is going to be an interesting era for the future stellar archaeology. And some of the current ongoing surveys are Hermes. This is at the Anglo-Australian Observatory, and this survey is behind a 4-meter class telescope, and it goes up to V magnitude of 14. So, it can observe dwarfs up to 1 kiloparsec, giants up to 15 kiloparsecs. So, this is also going to survey a large volume of the southern skies specifically. So, this is going to be a counterpart for SDSS. And with the data from Gaia, combining Hermes and Gaia, that is going to provide a 6-dimensional space phase information, both the positions and proper motion in all the directions, and along with the chemical abundances. So, this is going to provide a unique chemodynamic tagging of individual stars in the southern part of the sky. So, these are the ongoing surveys like SDSS, Hermes, RAVE, LAMOS, SkyMapper, and this is a photometric survey at CFHT. It focuses on a narrowband imaging at calcium K wavelength. So these are the surveys which are happening right now, and the upcoming ambitious surveys are foremost behind a 4-meter telescope, and MSC is a future 10-meter class telescope dedicated spectroscopic survey. And there is also soon, which this is going to come online, is the prime focus camera behind a Subaru telescope, 8-meter telescope. So these are going to survey very deep and very farther, because as we saw in the talk, as you go further and further, we are going to probe the outer part of the galaxies, which has contribution from accretion of the most primitive satellites. So we are going to see the unpolluted, or we are going to see a significant fraction of very low metal poor stars. So stay tuned. Thank you.